However, such capabilities is not happen like randomly. Most of the deep neural networks in the pre-large net model stage, people showcase is more a memorization rather than generalization. Memorization means I just memorize every patterns in the training data set. It told me this such kind of things is dog. So I memorize the features of the dog. So next time you give me an image to see whether it's a dog or not dog, I can answer you yes or no. Most of them are memorization. In the large net model field, people do the testing for its zero-shot compositional generalization capability examining. They will showcase that if your model is large enough to train on sufficient data, you can have a capability called emergent capabilities, which showcases the zero-shot performance of LLM models on the task, which you never seen it before and can do very well. So, which means language models, large language models, for the first time, gains intelligence, real intelligence, compared to like a hard-code pre-programming. However, it is very hard to iterate why it has such capabilities because it has so many parameters. So iterability or explanation for AI models is a super hot topic in the community, and no one has a good answer yet. So how to build it? We will discuss a little bit for how to create the transformer models, how to build the GPT kind of models. So overall, transformer models is a stack of a series transformer block. Each block can be a decoder of models, which I will introduce you later. And the input will be the sentence, the words. Each words will be converted into a vector. And the vectors will be further input to the models, like produce the next layers of your embedding again and again. Okay. And what the encoder network looks like? It contains two components. First component is self-attention. I will introduce in detail later. Second component is called feed-forward layers. Basically, we understand what is a feed-forward network. Just a feed-forward network, which is a multi-layer perceptrons, which is a few layers of linear regression plus some nonlinear operations. Okay. So, and what is self-attention? Let's go to. So self-attention or attention is to compute the word-to-word relationship, to word-to-word coefficient, word-to-word scores. Okay. So basically, imagine there is input, and then it's a sequence of words, and each word you will have embedding, and along with a sequence, you will have a sentence, you will have a matrix, right? And after that, you will do the feature transformations and produce three matrices. These feature transformations is three different fully connected layer or perceptron layer. A few of them, or a few of layers of like a multi-layer perceptron or feed-forward network. Okay. And it has the weight matrix, for example, WQ. It will multiply with input matrix and produce a query matrix, Q. Okay? And again, we can do like similar feature transformations, which is WK, which is a key matrix, transforms input to another matrix called the key matrix. And we will also have another third multi-layer perceptrons, which is different with the previous two, called like a value matrix, WW. WV, which will multiply the input and produce the value matrix. After that, the Q and the key will multiply together, which can produce like a matrix L times L. We call it like attention scores. Okay, it captures like word-to-word coefficients. After that, you will multiply the attention scores to the value matrix, basically to do some weighted summations for each position. In the end, you can do some like functions like softmax kind of things, or compare them together and output the final transformed like matrix. And usually we will do softmax in this like stage, and like just calculate the cell scores, attention scores times softmax, and use it as attention scores. It comes with V matrix. So what attention did, it actually will compute how this sentence, one word is associated with different words. So for example, for this example, you can visualize the attention scores between each word here and all the words here. The darker means there is a strong correlation, and the shallow color means there is like a weaker correlation. And then you can do similar ways to cross all the attention modules. Yeah. So after the cell attention, the second module is called feed-forward network, which you probably are quite familiar with. Basically, for each position in the sequence, you will have linear transformations, which is Wx plus B, right? This W1 is the first layer, the weight of the first layer of MLP, right? After that, you will do a nonlinear activation, which is a ReLU activation here. If the value is smaller than 0, then it's 0. If the value is larger than 0, then it's identical, right? And this matrix will times the weight of second layer W2. After that, it will plus B is a coefficient, and is a bias. So this is a feed-forward network. The parameters in the feed-forward network will be W1, W2, B1, and B2. Okay, so let's see. The parameters in one transformer block, what is it? Basically, for the multi-hat attention, for each hat, you will have the weight matrix WQ, WK, and WV. And for the FFNs, you will have more parameters, W1, WQ, which is the first layer, second layer MLPs. For the feed-forward networks coefficient, together with B1 and B2, which is bias parameters. And okay, now you already know what is within each transformer block. And for a transformer, you will repetitively stack them together to larger models. Okay, and the embeddings, as we mentioned, is also learnable, right? Because it's a 2-layer of MLP. We are learning the mappings project from 0, 1, 100 embeddings to a continuous embedding, which is more informative, right? Okay, and transformer encoders will stack together and performs like pre-training and fine-tuning. So what's the task? What is task for pre-trainings? First one is next pattern prediction. And usually in the natural languages, they will not only consider next token prediction, but also consider next sentence prediction. Next sentence prediction is much easier compared to next token prediction. Why? Next sentence prediction just predict whether the next sentence is the next sentence. Whether one sentence is the next sentence, yes or no, right? And also there is something called mask language modeling. Basically, say masking some words here and predict why there's words, why there's a word it is. Basically, when you have the embedding layers, you can attach a prediction layer and output the final values you want. This is a pre-training. And for the fine-tuning, so the difference between pre-training and fine-tuning. Usually, the most straightforward difference is pre-training will have a lot of data, and the fine-tuning usually only have a small amount of data. It seems very like hard to recognize, okay? But let me tell you more about that. Usually pre-training you need to have like hundreds of millions, 100 even billions level of data. However, for such amount of data, it's very hard to produce semantic labels. Imagine, if I give you like 1 billion of images about dog, cat, different animals. If you want to produce a label, which means you need to hire hundreds of thousands of people to see the image and label the image. It's almost impossible because it's too expensive. Which means usually for the super huge pre-trained data set, it is unlabeled. If it is unlabeled, how could we train this model? Your model, you always need a supervision, right? You need to have a prediction, and the prediction will minus the label to produce an error. The error will generate the gradient will update the model. So if there is no label, how should we pre-train the models? There are some smart people think, whether I can do some unsupervised learning without supervision. One of the famous technique is called self-supervised learning. Basically, I can create some pseudo label by myself. Then, what is some popular options for self-supervision? For example, mask language modeling. I mask one word to predict it. I like apple. I mask apple. Something blank, apple. Probably I eat apple. I like apple. I hate apple. I buy an iPhone, right? So, but you will have the label, right? Because you mask it, you know so what is under the mask. So in this way, it produces labels. Also, next token prediction. I know the next token is, so I can the word in next token automatically be a pseudo label for next token prediction task. Also, next sentence prediction. Give you a paragraph. You know what is next sentence, right? I give you 10 sentences. Ask the model to predict what is next sentence. You can do that. However, usually for such kind of tasks, cannot have a strong correlation to the semantics. The task I provide to you, but actually in the testing time, I hope the model can do automatic code programming, can do automatically write me an email. I want to skip tomorrow class. I want to write an email to my advisors to see whether I can ask for leave, right? Model cannot do that. They cannot build semantical related predictions because they are not touched by semantic or meaningful labels. This is why we need fine-tuning. So for fine-tuning, means I can use a small amount of like data, which is like a few thousand, tens of thousands, because it's small. So I can create semantic labels as I wish. If I want to predict whether it's like eyeglasses or a computer. I just collect image to label its eyeglasses, computer, eyeglasses, computer, eyeglasses, eyeglasses, etc. If I want to predict whether it's a car or a bicycle, I just take images and label it like a few thousand. If I want to do automatic code programming for Python, I just write some code and label it. It is a definition for variables. It is initiate the instance. It is do the logistical operations. It is print kind of things. Show examples, right? Then you can fine-tuning the model. And fine-tuning model, actually you turn in a general purpose model to a specific domains. This is called fine-tuning. Hope you have a rough idea. It only needs like a small amount of downstream data for the training, and only have like a few layers that can be trained for different tasks. So usually, you can see for different tasks, like natural language inference, reading comprehensions, codebook QAs, and different color indicate the different method. Zero shot means you do not do any fine tuning, just do the inference. Few shot means you only give it like 3 example, 5 example, 10 example. Full model fine tuning, language model fine tuning means you give it like thousands of the examples. So they show significant performance difference. Fine tune, more data, more fine tuning, definitely can do a better job. Now we will go to the sections to introduce some of advanced transformer architectures. We have encoder NLA transformers, decoder NLA transformers, encoder